Now we want to know, given that the optimal balance of investment depends on ecology, what kinds of ecologies select for what kinds of parental care is the next question. So we'll look at selective environments. So this is E.O. Wilson, who is a massively eminent entomologist who produced a huge book on several famous books. He's an ant biologist, so he produced a book called The Ants, which is the key Bible for the ants, and also produced a book called The Insect Societies, which is the first attempt to really get a handle on social insect biology. But his book called Sociobiology suggests that there are 4 major prime movers that select for parental care in an evolutionary sense. So the 4 prime movers are stable and structured environments, so things that lead you to have a slow life history, to produce few offspring at each bout and invest a lot in each one. If they know, if an organism knows that the environment is going to be kind of safe and stable and it's relatively safe to invest a lot in one offspring. You're not constantly running away from predators. The offspring can take a long time to develop. Resources are predictable. That will lead you to invest a lot into one offspring. But then at the other end of the spectrum, you have harsh environments where you need protection against the elements. So where protection is required against maybe harsh abiotic conditions like desiccation, or high levels of predation where you need to protect offspring from predators. Or if you exploit scarce or particularly specialised resources that need defending against competitors. So 4 major things which select for parental care. Those have remained quite theoretical for many decades without very much proof, but we'll come to that in a bit. But Hope Klug and Mike Bumsall are 2 people that like to model mathematically how selection pressures work in nature, and they really like working on parental care. So they did a couple of theoretical models of how different patterns of life history would select for different parental care behaviours, and they found that some specific life history features would select for parental care, one of which is a slow rate of egg maturation. So if your eggs mature slowly, and that kind of corresponds to Wilson's stable, structured environment. And they also found that you get selection for parental care if there is a high rate of offspring mortality in the absence of care. That stands to reason. If offspring need defending against something like harsh environments or high levels of predation. And also if there's low adult survival. Okay, so those theoretical conditions correspond to the hypotheses that Wilson produced. So that's a bit about the different selective environments that kind of select for care. You've got really stable environments at one end, but really harsh, unstable environments at the other end, and kind of in the middle you've got selection for no care. So what about the costs and benefits of parental care? We've kind of talked a bit about parental investment, but there are different kinds of costs and benefits. So how much, the costs and benefits will define how much care is appropriate to give. And if you think about a very simple kind of model of how your benefits and costs of care change depending on how much you invest in each offspring. Here is me and my offspring. That's Matilda. I told you this is an old lecture. She's 6 now, so I can't quite carry her like that. She has a little brother who's about that old. But imagine I invest effort in feeding her biscuits. Right, so the more biscuits I give her, now I have to go and forage biscuits from the environment. And if I keep feeding Matilda biscuits, she's going to get benefits initially, but after a while she just can't eat any more bloody biscuits, right? So the benefits to her, like there's no, like beyond like 5 biscuits, she's not going to get any more benefit from me feeding her biscuits. The benefits are going to asymptote. Okay, but it still costs me as much to get each biscuit. Each biscuit is the same amount of effort for me to go and get. So beyond a certain point, there's just no point in me expending effort getting more biscuits. Right, so you can see from that example that there is an optimal point at which I just stop getting biscuits and do something else. Right, and that point is where, the optimal point for me to stop is where the benefits minus the costs are at their maximum. Okay, so here is the benefits minus the costs. And that point there, where the benefits minus the costs are maximum, is where I want to stop getting biscuits and start doing something else, because that's the point at which you start getting less benefit for each biscuit. Okay? So now we need to know a bit about those costs and benefits. Oh yeah, so note that these costs are kind of measured in terms of how many more offspring I can raise in this brood. So we'll start with costs. What kinds of costs does parental care bring? We're going to focus on costs. So there are 3 main kinds of costs. There's a survival cost. So one good example of that is the Miles et al. Paper. This is a beautiful, beautiful experimental study where they took a sample of pregnant lizards, and in some of them they devised a surgical procedure where they surgically removed some eggs, and then in a sham procedure in a control group, they surgically removed them and put them back again. So they've got 2 groups, one of whom have had their eggs removed, and others of whom have had their eggs removed and then put back again. And the ones whose eggs were removed had better endurance, better survival, like measured better on a whole host of performance tests in the field. So they get away from predators better, etc. So in other words, having eggs is a cost. Like you get worse predation, you get more predation, less better endurance, etc. So there is a survival cost to performing parental care in the form of carrying eggs. There's also an energetic cost. So Gustafson and Sutherland experimentally cross-fostered eggs among nests, and they increased the clutch sizes of these collared flycatchers experimentally, and they reduced some others, and they found that the ones where they increased the number of eggs had fewer eggs in the subsequent season. So it's energetically costly to be feeding all of those offspring from this season, which means that you can have fewer eggs next year. So that is a cost of parental care. And then finally, there's a mating cost of care. So Temmink stints, well, I think we met Temmink stints in the first year when I gave a lecture on behavioural ecology. But so you've got males which can choose to abandon their eggs, or they can choose to care for them. And abandoning their eggs involves the opportunity to go and mate again. But if you choose to care for your eggs, you lose out on the opportunity to mate again. So this Thompson et al. Paper shows that males that choose to care for their eggs, depending on the amount of mating opportunities in the environment, can stand to lose a lot of mating opportunities if they choose to care. So the survival, energetic and mating costs of care. And there's quite a lot of evidence that animals will tailor the amount of care that they give. They're not kind of universally love, like they're not kind of unconditional love towards their offspring. They're very sensitive to the costs and benefits, and they will do whatever behaviour results in the most surviving offspring. So if you reduce, my old PhD supervisor, Andrea Manica, did an experiment where he experimentally removed some of the eggs in the clutch of these male scissor-tail sergeants. He found there's this threshold level at which the guarding male decides, screw this, like it's not worth hanging around to care for these few eggs. And at that point, the male decides to eat the entire clutch to regain that energy and then use that energy to go off and search for more mates who can give them a bigger clutch of offspring. So very, very sensitive to the cost of current brood. Also, females, on the other side, females will expend more or less energy depending on the brood, depending upon the value of the mate that they've mated with. We'll put some beans on this. It's called the differential allocation hypothesis. Nancy Burley showed that in zebra finches. If you experiment, like for various reasons, which we will get into later in the lecture course, females prefer to mate with males that have been given a little hat. Given that we know females prefer to mate with males that have been given a little red hat, if you give a bunch of males a little red hat and then allow them to mate with females, the females will put more effort into the eggs that they lay. So females will tailor their reproductive investment depending upon the quality of the male. It's called the differential allocation hypothesis. Very nice. Then there is... so that's tailoring your care to the value of the current brood, okay, what you can expect from the current brood. But there's also, animals will also be sensitive to the future value to how much residual reproductive value they've got left, and they will tailor their current care based on what they can expect in future. So, for example, this Ball, Shine, Earn and Earn paper found that St. Peter's fish will be sensitive to the mating opportunities in the environment. So both sexes, male and female, will desert their current brood if they think they can get a better mating opportunity elsewhere, i.e. if there are enough mating opportunities in the environment. A bit similar to those Temming's stints. And then also there's something called the terminal investment hypothesis, which is if you're sensitive to the fact that you've got less residual reproductive value, if something happens that means that you think you're going to die soon and that your future broods are less important now, you will you'll reduce the weighting that you put on future broods and you'll increase current broods. So the prediction is that if you think you're going to die, you'll blow all your investment on this brood. And that's the case with burying beetles. So burying beetles can have several broods during their lifetime. But if you experimentally infect them with bacteria, they will increase their parental care investment. So you can animals tailor their care to the value of current and future broods. So